Welcome. Today we'll be doing a brief overview of transistors. If this topic interests you, I highly suggest taking ECE 2280. Today we will learn about what transistors are, some examples of different types of transistors, and how we can use a transistor in a basic circuit. So the big picture is the transistor actually has 3 terminals instead of just 2. So one of them is kind of a reference terminal used by both. And then we have an input terminal and an output terminal. So this is a semiconductor device. And so it's made with semiconductor materials in a nanofab lab. And we dope the materials either with extra electron carrying atoms or extra positive hole carrying atoms. Some common examples of what we use transistors for are amplifiers or electronically controlled switches. We'll see both of those later in this lecture. So one type of transistor we'll be talking about today is the bipolar junction transistor, or BJT. As you can see here, it's kind of looks like 2 diodes shoved together in terms of its semiconductor materials. We've got 2 NP junctions inside of there. And the N material is that negatively doped semiconductor, and the P is the positively doped semiconductor. And then notice each terminal has a name. So we have the base, collector, and emitter. So the emitter is kind of the shared ground I showed in the previous image. The base is the input, and the collector would be essentially the output. So we can actually create these transistors in the nanofab lab. So down below at the bottom is a picture of how the different layers of material be set up on a substrate to create this transistor on nanoscale level. The other type of transistor we will talk about today is the MOSFET, or the metal oxide semiconductor field effect transistor. So these are similarly built. As you can see, there's 2 NP junctions again. But this time, we actually have different names for the different terminals. So the source is kind of the shared ground. Gate would be the input, and drain is the output in a sense. And again, we can grow these in the nanofab, and there are some nanoscale pictures on the right of a transistor. So each of these types of transistors also comes in different flavors, depending on how the semiconductor materials are put together. So we can either have the positively doped material in the middle or the negatively doped material in the middle. And these will then act in different ways. So we normally put the arrow down on the emitter, and then the direction of the arrow is kind of a reminder of which way the current would flow when this transistor is in a working configuration. So remember, base is kind of our input, and collector is the output. So what happens here current-wise will affect what happens here current-wise. Similarly, the MOSFET also comes in different flavors. And again, we have some arrows reminding us which way the current flows when it's correctly configured and on. And this here is the gate. And when we apply a high enough voltage there on this one, that will turn on this transistor effectively and allow current to flow over here. And with this one up here, this little knot symbol is a reminder to me that this gate will actually turn on when the voltage is low at the gate, and that will turn on a connection here for current to flow. So yeah, here are 2 different models that can be used for transistors. It really depends on what regime you're working in, what type of transistor you're working with, etc. So one way we can use transistors is to amplify current. So in this case, we can model the transistor, and oftentimes we'll use BJTs for this, and that's why we have the base, emitter, and collector. So we'll model this as a little current flowing in the base, creating a big current flowing through the collector to the emitter. So that way I can take a little current signal and amplify it to be a big output current. Similarly, I can also use a transistor as an electronically controlled switch. So often MOSFETs are used for this. And so in this case, the gate is our input. So if I apply a high voltage here on the gate, that essentially turns this transistor on, meaning we flip a switch and cause a connection here. So the switch flips, and there's a slight resistance inside of this transistor. And so by applying a voltage, we basically allowed the circuit on the other side connecting the drain and source to connect and create a complete circuit, and therefore we turn something on. And that's why it's called an electronically controlled switch, because I didn't have to physically flip the switch. Instead, I just applied a voltage at the gate. So we can also look at the IV curves for transistors. You can see that these are nonlinear devices, but if I look at various regions, I can create approximations for those regions that are easier to work with. So over here, I've got a region where I can draw a straight line to approximate the curve. And then this region over here, I can also draw a straight line. So this straight line with a slope reminds me of a resistor. And this flat line here kind of reminds me of a current source. Well, that's really interesting because on the last page, right, I had one that was acting like a resistor, and I had another model that was acting like a current source. And that's indeed what we see here. Is so if I'm working with a BJT as a current amplifier, I'm working in this region right here. And you can see the different curves represent the input current. So as the input current increases, the output current increases. And notice that I'm inputting like 20 microamps here and getting out something like 15 milliamps. So I'm multiplying by somewhere between like 100 and 1,000 amplification-wise. And then in the case of the resistor with the MOSFET, I'm actually working in this region where it looks like a resistor, that straight sloping line. And again, that matches the model on the last page, which was a switch. So when the switch is open, I'm down here, just plain old off. And then when the switch is flipped, I'm a resistor over here. And so depending on what transistor you're using in what region, we have different names for it, right? So the MOSFETs being used as electronically controlled switches, they call this region over here the saturation region because they're not working with it. Similarly, the BJT being used as a current amplifier calls this region over here the saturation region because that's not the region they're working in. So notice they use the same term to represent different regions in their specialized IV curves. So that is all about how transistors work, and the next video will explain how to calculate a circuit with one of these and applications of circuits with transistors.